Right, what we're doing today, we're doing computing A-level / AS level / probably GCSE to some extent, and we are doing the structure and function of the processor. And this is probably going to be 1, 2, 3, 4, whatever flashcards, and it would also be like what would it be? So we're going to have this part be notes, and we're going to have the other half be like drawings and or animation to help. So while we're getting started, please like, sub, etc. So the first thing is, I feel like this is going to be more notes than anything, the ALU. Okay, we don't need to write that. So that's basically the arithmetic and logic unit. The ALU is responsible for all arithmetical and logical operations. So that basically means anything that like requires thinking, so stuff like if statements and or anything that requires maths, the ALU will do. These do include all maths and would include stuff such as Boolean, XOR, and NOT, etc. So do we do and, not, or? So and, not, and or. So and is when both cases have to be true, not when one case is true it is made false, vice versa. Vice versa basically means the other way. And or, either A or B must be true. So that is literally the and or, not, and that is the logical operators part of this. So the control unit. The control unit is a component of the processor which directs the operation to the CPU. So basically it does 5 main things. So let's write that down. 5 main things. So we're going to try and concise this as much as humanly possible. So control activities, so that's inside the CPU. Flow of data inside the CPU. Next instructions, decode instructions, and store results of data back into the memory. So we could go through all 5 of these. So control unit does direct operations to the CPU, sends them to them, and the 5 main things it does is it controls the activities of the CPU, controls the flow of data to CPU, processes the next instructions, decodes instructions, and stores results into the memory. So now, registers. These are memory cells which work at high speeds. They're mostly used to temporarily store data. That is the main function of them. So there are 4 types of program counters that everyone needs to know about. So 4 types of registers, and one of them is the program counter. So this holds the address of the next instruction that needs to be used. So that is program counter. That is a terrible name for it. It should theoretically just hold the amount of programs that's been done. So accumulator, which holds total results from calculations. So say you're doing maths, the number you've gotten to so far, that would be stored in the accumulator. Memory, address, register. So this basically holds the address for the location that is to be read or written from, holds address for reading and writing. Next is memory data register, and this would temporarily store the data that has been written from. And then current instructions register would hold the thing which is currently being done. So in a way, these all like work off of each other to be able to function properly. So obviously, program counter holds the address for the next instruction, the accumulator holds results. They all hold something. So the memory address holds the address where you need to read and write from, and the memory data register holds the stuff you actually get from being able to use the memory address register, and current instructions register would literally just hold what's currently being done. So buses, there are three types of buses: data bus, address bus, and control bus. So buses, so these are mostly parallel wires which would connect two or more components to one another. Simple. And that would be inside the CPU. So data bus, come on, this one's very self-explanatory. These used to transport data and instructions. Address bus, this would be used to transmit the memory address to tell you where data is being sent. And control bus, this would be used to send control signals between external and internal components. So this control bus would need the address and data bus to be able to actually get the data transported to it, to be able to transport to and from, and would also need the address bus to be able to have the memory address to specify where the data needs to be sent, etc. So now, assembly languages. This is stuff like, obviously, Little Man Computer. That was class. So, assembly languages. So, this uses mnemonics to remember / show instructions. For example, stuff like add would be addition, etc. And this would be as close to machine code as you can get, because obviously computers run on machine code. So obviously assembly languages are a way to be able to actually show humans how close you can actually get to machine code without actually making it so we just don't get it. So pipelining. So this is the process of finishing the fetch, decode, execute cycle. So that is basically, but that would actually be called the fetch, decode, execute cycle. Pipelining is when process finishing. This would be 3 times over, because you have to do it 3 times. So basically what it does is it holds the data in a buffer until it's needed. So basically what it's actually used for is it's used to reduce the amount of CPU which is kept not used. So as long as you have space in the CPU, you might as well just use it. So the fetch, decode, execute, cycle, and registers. So the fetch, decode, and execute cycle. So basically, wow. Yeah, fixed. So basically, this is the fetch bit is the most you need to remember. The other two you don't really need to remember much. So first of all, the fetch would get the address from the program counter. It would then copy it to the MAR. We are literally using mnemonics for this. So the instructions, that's not useful instructions, would be held in that address, and it would be copied to the MDR using data buses. Then the program counter would increase by 1 because you've done the first part. So decode, the contents of the CIR would be split up into smaller chunks to be used later, or to be solved by itself or more in smaller pieces so it's easier. And execute, the decoded instruction would be run. Simple. So that is the first part of this, and now we probably won't fill this. Let's be fully honest here, we have like 1 or 2 more things left in this entire thing. So there are what affects CPU performance. So clock speed, this would be the number of cycles per second. So basically, when you have a higher clock speed, this would mean more things would be processed in a shorter amount of time, because more data would be getting moved from one place to another. Simple. So that is basically the full premise of clock speed. Now, the number of cores. The number of cores. This would be a solo processor which would be able to run its own own cycles. So basically that would mean that the overall time would decrease as more cycles would be able to be run in a short amount of time, and due to this it would mean that you should be able to complete tasks quicker. But the only downside is that is not always the case. Sometimes some other issues may or may not happen, and due to that you should not only rely on 2 cores or 4 cores or however many you want to use. And now cache memory. This is very expensive memory, which is also very quick. It is the CPU's onboard memory, which would make a pathway to be able to limit the time taken for instructions to reach the CPU. So that would theoretically mean everything is very quick, but obviously the issue comes up that is also very expensive. So now architecture, there's the final. So von Neumann, his architecture. So he made the basic components architecture for which there is shared memory and shared data between all of the components, and this would be built upon the stored programming concept. And then there is the Harvard architecture, which would mean that you would have physical separate memory. This would be better because it would mean that you would have different stores for different characteristics, and that would mean that everything would be categorized into their own sector, thus meaning that you can optimize the efficiency for the memory to be able to make them more productive for real world situations. Simple. Wow. So that is literally the finish of structure and function processing. So the entire of topic 1 of A-level computing. Well, 1.1.1. There's also types of processors and output, input and storage. So those will be next. Thank you, Pete.